Hello, project data scientists, and welcome to another magical project data science course. This one is really exciting because this is a mini course that's focused on giving you an introduction to neural networks. Neural networks are obviously a huge field in machine learning and artificial intelligence these days. There is a ton to cover with regards to neural networks, which is why it can be so intimidating to get started. So that's exactly what this project is for, is helping you get started with neural networks in a very easy, very low risk way. So we are going to be doing that using one of the most common kind of introductory neural network projects, which is digit recognition. So let's go ahead and take a look actually at what we are going to be doing. So let me drag over a Chrome window here. So let's look at the MNIST dataset. So basically the MNIST database, let me open this Wikipedia page here. So, blah, blah, blah. This is a large database of handwritten digits. And the task is very simple. The task is basically just, how do we write an algorithm? How do we train a model to be able to distinguish these digits from each other? So the problem statement is very simple, right? It's we have a bunch of zeros, we have a bunch of ones, we've got a bunch of twos, threes, fours, fives, etc. And we want to be able to distinguish between them, or we want to be able to have a model distinguish between them. So it's a very simple problem statement, which is why this is kind of a good beginner project here. But it's also very interesting because once you start getting into the code and thinking about, like, how do we do this, it's not actually a trivial problem for computers. Something that we might think of as human adults as being very easy actually has a lot of complexity going on underneath. So that's why this is a great project to start with, and because this is a data set where you can really see neural networks start to shine a little bit. And there are more complex data sets like like ImageNet is one that definitely gets more complicated. You've got a ton of pictures, and they're about a lot of kind of real life things, and so distinguishing that is even harder. So that's why starting with something like digits is a little bit easier here to get started. And you can start to tackle this problem without neural networks as well. And we're going to do both of those. We're going to start without neural networks, and then we're going to introduce neural networks, and that's how we're going to approach this. So we are going to get started like I usually get started with data science projects, and that's by opening up a terminal here. Let's see, let's do new window. Let me drag it over here. It was on my other screen. And I'll go ahead and full screen this. And let's create a new virtual environment. So I am using Conda, which is a virtual environment manager and a package manager from Anaconda. And if you do not have Anaconda installed, I would recommend installing MiniConda, which is kind of a small version of Anaconda. So you just come here to this page, Google MiniConda, download whichever one of these is right for you. And you can read more about MiniConda and Conda if you want. But basically what we're doing here is we're going to create a new virtual environment. And I might call this something like, what do we want to call this? Let's call this MNIST Jupyter course. And Jupyter, because this is a mini course here, we're going to do the entire thing in a Jupyter notebook, which is kind of a nice, easy way to get into it without having a bunch of Python scripts floating around. So we do conda create. We do this -n and then name our virtual environment here. And then let's go ahead and pick a few packages that we want to install. So we want to install, well, first, I'll put Jupyter here because we definitely want that. We want pandas. I'm going to put NumPy here. Even though NumPy is installed with pandas, I'll just be explicit about it. Let's go ahead and install scikit-learn for all of our machine learning modeling stuff, other than the neural networks, which we'll install with TensorFlow in just a second. Matplotlib for data visualization, Seaborn for a little bit fancier data visualization. And let's go ahead and start with that. So this will collect all of the information about all these Python packages, these Python modules that we're installing here. And it'll let us know what it's going to install. So it's going to install all of these. And the reason why you might be seeing so many packages, if you're wondering why that is, that's because we're also installing all of the Python packages and the modules that these things up here need. So, you know, if we're installing pandas, well, pandas might also need, pandoc here. It might need pandoc filters. One of our plotting libraries might need pigments in PyQt. So we're installing all the dependencies as well. So I'll go ahead and type Y. Let's get this installed here. It'll take just a minute. All right, so we have our conda virtual environment installed. So a virtual environment, by the way, if you're not used to using these, let me just Google this really quick. Python virtual environment. So there are different ways to do this, but I like conda because it's pretty simple. It's pretty easy for people to get started with. So, all right, so let's read this here. Python applications often use packages and modules that don't come as part of the standard Python library. That's what we're doing. You know, we're using pandas, we're using scikit-learn. These are additional Python packages. And applications sometimes need a specific version of that library. And here's kind of really the core thing right here. This means that it may not be possible for one Python installation to meet the requirements of every application. If application A needs version 1, but application B needs version 2, then your requirements are in conflict. And this can get really messy, and it's a very common thing whenever you start dealing with a bunch of different Python scripts. You know, if you've got a bunch of little different applications that are interacting with each other and they need different versions of things, well, that's going to create conflict very quickly. So that's what a virtual environment does, is it takes all of our Python packages, it takes our Python installation itself and wraps it up into a nice little folder. So let's show that really quickly. I'll type, so let me type which Python. So this is going to show me which version of Python I would currently run if I run just Python. So currently, if I just type in Python and hit enter, this is Python 3.7.3, and it's coming from this folder, Anaconda 3 bin Python. Now let me type exit. Now, if I activate the virtual environment that I just created, so MNIST Jupyter course, now let me type which Python, and you'll see that I'm pointing to a different version of Python. So I am now pointing to Anaconda 3 envs, and now this is where virtual environments are kept using conda. MNIST Jupyter course bin Python. So this is a totally different Python installation, a totally different Python executable, and all of the packages and all the modules that we installed are in this folder here, this MNIST Jupyter course, which means that we can install whatever versions we need inside this virtual environment, and it won't be in conflict with anything else. And if we royally screw something up, if we blow something up here, then we could just delete this and start over, and that would be totally fine. So I have now created a virtual environment, and this is good. So this is kind of where we're going to live for the rest of the time, is in this virtual environment. But we're actually going to be doing our work in a Jupyter Notebook here. So I'm going to launch Jupyter Notebooks in just a second, but first we need to install one more thing, and that is TensorFlow. So If you know anything about neural networks, you've probably heard of TensorFlow, and if not, really just what you need to know is that this is one of the most popular neural network libraries. TensorFlow is an end-to-end open source platform for machine learning, and a lot of the state-of-the-art neural network stuff these days is written in TensorFlow. There are some other packages like PyTorch is another big one. But TensorFlow is what we'll use for this course. So if we go to install here, let's scroll, let's see, where are we? Okay, here we go. So requires the latest pip. I think we should have that. We should have the latest version of pip. I'll go ahead and copy this over anyway. So this is a Python package manager. All right, requirement already up to date. So we're good. By the way, if I type which pip, you'll see that pip is also an executable that is inside of this virtual environment. So that's perfect because we want to use the version of pip that is going to install things, because pip is an installation manager. So this is going to install things into our virtual environment, which is good. So now we go over here, pip install TensorFlow. Let's do that. And it's just going to collect everything that we need and install it. So let's wait a minute for that to complete. All right, so after a ton of printout here, basically what we just did was we installed TensorFlow and all of its dependencies, which you'll see here. So we are good to go. So what we are going to do now is let me go to Documents, and I'm going to create a new folder. I'm going to make a directory, mkdir here. We're going to make a directory where all of our files for this course are going to live. So I'm going to call it MNIST Jupyter course. Let's just call it that. So I'll cd change directory into our MNIST Jupyter course here. Now, if I do ls to print out what's in this directory, well, there's nothing. That's because we just created this folder. So there's nothing in there currently. So now we are going to run Jupyter Notebooks, and this is where we're going to be doing all of our work, is inside of a Jupyter Notebook. So I use the ampersand here to run it in the background so that if I needed to, I could come back into this terminal and still do things if I needed to. So that's what that ampersand does there. All right, so it looks like it popped open on my other monitor. So I'll drag it over here. So, all right, perfect. So you'll see that we have a new version of Jupyter Notebooks running here. And I can come over here to this. Oh, and by the way, we launched inside of this new folder here. So that's why, if you click home, well, our home is this folder, MNIST Jupyter course. So I come back over here to Jupyter Notebooks. I can click New and Python 3, and this will create a new Python 3 Jupyter Notebook inside of our virtual environment and inside of our folder. So let me title this something. What do I want to title? Well, maybe I'll just call it MNIST Jupyter course using neural networks. Maybe we'll call it that. All right, perfect. So one of the first things that I like to do inside of a Jupyter Notebook, and by the way, if you haven't used Jupyter Notebooks a ton before, there's basically just a couple things to know. One of them is that you have cells that you can run Python code in. So you can say like hello world, print hello world, and you can do 2 times 2, and that equals 4, and you can have variables, x equals 10, and let's look at x and all that kind of stuff. So you have cells that are code, and then you also have cells that are just text. It's cells that are markdown here. And so I usually just use the shortcut M, so I'll type the letter M here. And now this is a markdown cell. So here's where I can put some text. I can also put lists of things. code formatted things like x equals 10. No, actually, let's put the code formatting there. We can do bold text. We can do italic text, etc. And now if I run that cell, so previously whenever I ran cells, it executed the Python code in there. If I run this markdown cell, well, now this is just kind of a nice explanatory text block. And so the reason why this is cool is that we can not only have code, which we run in cells just one at a time, but we can also document that code as we go along. So that's Jupyter Notebooks in a nutshell. There's a lot more here to that we can do with it, but for now, that's what we're working with. So one of the first things I like to do in a new Jupyter Notebook is I'm going to run this which Python command, and this exclamation point here tells Jupyter Notebooks that I want to run a bash command. I want to run a terminal command here. And we're doing the same thing as we did before. We're just making sure that we're in the right version of Python, that we're in our virtual environment here. So I like to run this at the beginning of the Jupyter Notebook just to make sure that that's true. I'm going to load an extension called auto reload here, and I'm going to do matplotlib inline, and these percent signs here just tell Jupyter Notebooks, hey, we're using a special Jupyter Notebooks command. This isn't something that you would see in normal Python code, but this is kind of Jupyter Notebooks syntax here. And if you want to see what these do, feel free to Google them. I'm not going to spend too much time on them here, but I like to put them at the beginning of every Jupyter Notebook. I think they're really helpful, and I would recommend that you do the same. But yeah, definitely Google around, kind of see what those do. So now I'll create a little markdown cell here, and I'll say imports. And then the way that I like to structure my imports is we've got our standard imports, we have our third-party imports, and then we have our local imports. And so standard imports, this might be something like OS, like operating system. Third-party imports, well, we're going to need pandas, and then we typically import pandas as PD. This is our library that we use for looking at our data and dealing with our data effectively, kind of in like a nice, easy way. We can almost look at data like you do in Excel, just like rows and columns. So I'll go ahead and import NumPy as NP. This is typically how you do this, and this is the main library that is underneath pandas here that does all of the heavy lifting, does all the actual number crunching, and it's got a lot of helpful functions in here as well that we might use. Now for plotting, let's import matplotlib.pyplot as PLT. That's typically how you do that. And we'll import Seaborn as SNS. And let's just go ahead and start with this stuff. I'll go ahead and run this. And then for plotting configuration or plotting config, I like to do sns.set. That just makes the plotting a little bit prettier. But if you haven't used these libraries a ton and you're wondering what the heck is going on, don't worry, because we're about to start using these more extensively, and you'll kind of get to see, you'll kind of get to understand things through using them. So for now, just know that this is how I like to set up a lot of my Jupyter Notebooks. This is how you get the packages that you need to work with in here. And now we can move on to the next step, which is loading our data. Okay, so before we load our data, we need to figure out how we're going to get our data in the first place. And how I'm going to suggest that we get our data for this course so there are a few different ways that you could get this data. There's the original, if we Google MNIST dataset, there's this original database that was published by Jan LeCun and Karina and other researchers here. So you could download these, but then you'd have to work through processing these yourself, which I believe on this site here, they say that it's kind of in a special format. So we want to do this kind of a nice, easy, quick way since we're doing all of this in a single Jupyter notebook for right now. So if we go to Kaggle and we Google Kaggle and then digit recognizer. So this competition on Kaggle, one of the nice things about Kaggle and also kind of one of the bad things about it is that their data is often very clean. So they take the data, they do some pre-processing, they get it into a nice format for you, and then you just end up with this nice clean data set that you can download and use. And sometimes that's not ideal, but for right now, this is how we're going to use it because this is exactly what we want. So if you haven't signed up for a Kaggle account, you're going to want to do that. And then I think you have to join the competition. And then if you go here, you can just click download all, I believe. And now if we click this, that will unzip it. And now we have this digit recognizer folder here with 3 different CSVs in here. So before we look at those, well, you know what, actually, let's go ahead and double click and open these really quickly, see what they look like. So this file is actually pretty big, 76 megabytes. Looks like it's taking a minute to open. I'm going to cancel that. Let's go ahead and move these into our project folder that we're working with here. So I'm going to go back to our terminal. And I'm going to say, let's move. So we're going to move, and I'm going to show you how to do this in the command line here. You could just do it here in this Finder window as well. So I'm going to move. Let's do tilde for the home directory. Let's go to our downloads, digit recognizer, and I'm going to move that into our current directory. So now if I do ls to list the contents of this directory here, you'll see that we have our Jupyter notebook that we're working out of, and we just moved our data into this notebook here. So ls digit recognizer, and there we go. We've got train.csv, test.csv, and sample submission. So our train.csv is where we're going to be spending our time. If you know about machine learning, you'll know that one of the cardinal rules is that you never want to evaluate your model on the data that was used to train your model, because that will result in overfitting. It will result in you being too confident about how good your model is doing. So that's why we have our training data that we use for training, and then we have our test data, which is used for evaluation. Although in this case, since Kaggle runs competitions, the test data is actually what you would use to predict on, upload to the competition, and then see how well you're doing. So at the end of this, I'm going to suggest that you do that you actually make the predictions, that you upload your predictions to Kaggle and see how well you do. But for now, let's get into the data. So we have our data set here, digit recognizer. So how do we get that into our Jupyter notebook? Well, it's very easy using pandas. We can just say df train, so df for data frame here, we're going to read in a pandas data frame equals pd.read csv. And I'm just going to give it the path to digit recognizer, the folder that we're currently in. So, you know, if I do a little ls in here, you'll see this is where we are. Digit recognizer train.csv. And then while we're at it, let's go ahead and read in our test data as well, so we can see how much data we have in each one of those. So let's look at dftrain.shape. This is a great way to get the number of rows, which is this first number, and then the number of columns. So we have 42,000 rows, so 42,000 images, and then each image, this looks like it has a shape of 785, so 785 columns here. So you might be thinking, well, what the heck does that mean? And this is something that we're going to get to in just a second. So For our df test, you'll notice that the number of columns is the same. Well, actually, we have one fewer column, so we have one less column here, and we have 28,000 images, 28,000 data points. So let's take a look at what our data looks like. So I'm going to do dftrain.head, which looks at the top 5 rows of our data here. So you'll see that our first column is actually the label. So this is the image. This is what numbered it is. So row 0 here in our data is an image that corresponds to the number 1. Now you might be thinking, you know, how the heck does that work? How does a row of zeros correspond to the image 1, to a handwritten digit of 1? Well, let's take a look at this a little bit more closely. So I'm going to do iloc 0 as a way of getting the first row here, and let's look at the values. And there you go. So by doing iloc 0, we look at the first row of our pandas data frame, and then by getting the values attribute, rather than it being I believe this is a pandas series here, and it doesn't show us all of the values, we're going to look at the NumPy array version of this, and you'll see that we do have a lot of zeros here, but then you actually do start seeing pixel values. So this is the value of the pixel, where 0, I think, probably means a black pixel that's turned off. And this goes up to like 250, you know, 253, 255, something like that. And that's where the pixel is totally turned, you know, you can think about it as turned on, or like it's white. So this, you can almost start to see a shape appearing here, but this is not how we actually want to look at the image. But this does give us a sense that there are values here other than 0. So before we look at the data, let's maybe split out our labels from our pixels. So the pixels are going to give us the image, and the label is the thing we want to predict. So we'll say our xtrain equals our dftrain, and then we're going to drop the column. We'll drop columns equals label. And what this will do is this will return a copy of the dftrain pandas data frame with the label column dropped. So this is going to return a copy. It's not actually going to be doing this drop operation on dftrain here. So, and just to show you that that's true, let's do that. Let's look at xtrain.head. And if we look at dftrain.head again, you'll notice that dftrain.head still has the label. xtrain.head just has the pixels now, and you'll see that we have 784 columns. And then our ytrain, this is going to be the thing we're trying to predict. This is our label. So we want to predict the number given the image in pixels. All right, perfect. All right, so enough of this talking about the data and looking at all these kinds of things. We want to actually see the data. You know, like I'm ready to see some data to start getting into it. So let's create a new section that says plot the data. And we're going to create some helper functions here that help us do that. But first things first, let's take a look at how exactly we're going to plot this thing. So this is one row of data. This is the pandas series version. You know, I did iloc 0. Let's get the NumPy version. Let's take a look at that. So this is a NumPy array. What are our dimensions here? Well, our dimensions are, it's a one-dimensional array, and there are 784 values. Now, I know from this data that this is going to be a square image. So I know that the square root of 784, well, that's 28. So this image is going to be 28 pixels by 28 pixels. So how do we get this into 28 by 28? Well, we can just take this NumPy array here, And we can call the dot reshape method on it. And we can say, okay, I want to reshape you into a 28 by 28 NumPy array. And now this is going to look a little bit messier because we now have a nested kind of array of arrays here. This is a two-dimensional array now. You know, if we call dot shape, then it's 28 by 28, which is exactly what we just told it to do. So we have a 28 by 28 NumPy array. And now we're going to use our pyplot. We're going to use our pyplot library here. So matplotlib.pyplot as PLT. And there's this function we're going to use called imShow. And let's look at the documentation for that really quickly. So plt.imShow. What is this? This displays an image, i.e. data, on a 2D regular raster. All right. So, and we pass in, what do we pass into it? Well, we pass in X. This is our array-like image data. You can pass in image data that is grayscale. You can pass in an image with RGB values, red, green, blue there if you want to plot a color image. So this is looking good. You can also pass in a CMap. This is a color map instance or the registered color map name, which is used to map scalar data to colors. So we have scalar data in this case. These are just numbers. You know, it's a 0, it's a 188. How do I visualize that? Well, this CMap is telling you how to visualize that. So let's use plt.imShow. So plt.imShow, and you'll see what this looks like here in just a second. Ta-da! There is our image. And remember, this is what? This is the number 1. Perfect. So we just plotted the number 1 there. Now this is plotting using, if we do, let's see, if we do plt. I think color bar. So this is plotting using kind of a warm reddish scale here. So what I want to do is I want to pass in CMap. Remember that deals with the colors. CMap equals gray. And now we've got that gray scale that I was talking about where 0 equals a black pixel and 255 equals a totally white pixel. Now, we don't need the color bar here, really. I'm going to add a title. Let's plt.soup title. Gives it a title over the full graph here, and we can say label. And I'm using an f string here, which means I get to use Python variables inside of curly brackets. So let's do ytrain.iloc0. And this is going to give us the label of what this image should be. So obviously, you know, we can look at it and say, well, that kind of looks like a 1. But now, you know, we have our title here that just tells us, okay, this is the number 1. You'll notice that we're printing out this text thing here. So that's just because this plt.soup title is returning an object. So this is returning like a txt object that we could assign here. We could assign this to a throwaway variable like an underscore. That's often one way to approach this. You can also just call plt.show at the end, and it gets rid of that output there because you've got kind of something in between this, which is returning something, and your final call in the cell. It's not really a big deal there. Doesn't matter too much. Let's turn off the grid. So let's do plt.grid false. And finally, let's also turn off the xtick labels. Oh, and you know what? Let's do that for the y ticks as well. Perfect. Now, you might be thinking, you know, if you haven't used matplotlib a ton before, you might be thinking, Stephen, how did you just know to call all these random methods on, you know, the PLT module here? Like, how did you know to do that? And the answer is pretty unsexy. I mean, honestly, it's just you look at something like this, well, let's say are X tick labels. So you look at something like this and you say, oh, I don't want these things. Like, I don't want the grid. I don't want these X tick labels. And you go to Google and you say, matplotlib, no X ticks. And you see that this is a Google search and it recommends that and you do it. And then you see Stack Overflow is usually the answer. And you say, okay, well, I want to remove my X ticks in a matplotlib plot. And you go here and you look at the answer and it gives you one answer, and you scroll down and you look for other answers and you try some of these things out and you see which one works best for you, and there you go. Like, honestly, that's how a lot of these things get answered. Is just kind of, you want to do something, trial and error. Or you could just go straight to the matplotlib documentation as well. You could look up matplotlib. You could go through the tutorials here. They've got a user's guide. They've got an examples gallery, list of plotting commands. Maybe let's check this out. So it's kind of it's a messy process of, you learn some things and then you don't know how to do some things, and you Google it and you look at the documentation, and you slowly figure things out, and you forget a lot. And so you have to look it back up a lot, and that's totally fine. That's all part of the process. So let's turn this plotting functionality into a function that can plot any image. All right, so let's do that. So I'm going to create a new Python function, just like a nice little helper function here, something where we don't have to type in all this stuff all the time. So maybe we pass in the pixels. Maybe we pass in a pixel row. Let's be explicit about passing in a row of pixels here. And we pass in a label. And then let's just copy all this code up here that we have down here. So we'll do plt.imshow, plt.imshow. So in this case, we're not passing in xtrain. We're passing in the actual pixel row. So maybe we'll assume that someone passes in the numpy array. And so we'll say pixel row. We'll reshape it, CMap of gray. We'll do the label here inside of our soup title, this title over the image here. And then I think this might be all that we need. Let's try it out. So let's try plot image, and let's try a different image maybe this time. So let's do xtrain.iloc. Maybe let's look at the index 1, and I'll also pass in, and let's make sure to do dot values to pass this in as a numpy array. And we can do ytrain.iloc1 as well. And there we go. We have a nice little plotting function that takes in the pixel row, takes in the label, and that's all we need to spit out an image here. So that is looking pretty great. Okay, so finally, one plotting thing that I want to do is I want to see a bunch of these images. So I'm going to really quickly create a function, and I want to look at, I'm going to say plot 10 images for each class. And here maybe we'll just pass in the xtrain and the ytrain data. And so I want to get kind of a 10 random images, or 10 images from each class, and I want to plot those in the same image. So the way that we do that is through this plt.subplots command. So we can say, okay, I want a 10 by 10. So I want 10 images for all 10 classes. And maybe I want, my fig size, maybe I'm going to make this a 10 by 10 image so that each image here has a little 1 by 1 square to get plotted on. And now I'm going to say this returns my figure and my axes objects here. And so this axis, AXS object, is actually going to be a list, or I think it might be a numpy array of the 10 by 10 different little plots that we have. So now how might we go about plotting this? Well, we could say, okay, we are going to want, for X train, well, I guess first of all, let's think about this. Let's go down here. So our Y train, if we look at that, okay, so we got Y train gives us kind of 0 through 9. So what if we wanted to get some images for the zeros? Well, we could say, okay, Y train equals 0. And this tells us true or false, where is Y train equal to 0? Well, now we can use this Boolean mask to index into our X train because these have the same number of rows, and each row in Y train corresponds to a row in X train. So we're going to use this Boolean mask to filter down our X train data. So now these are just the rows of data where the image is a 0. And if we want the first 10 rows of this, then we can do iloc like we've been doing before. And, previously we've been doing like iloc 0. Well, now let's go up to the 10th image here. So this is the first 10 images where the image is a 0. And now if I call dot values on this, then we get the NumPy array version of that. So let's start here. So we'll say for val in range 10. So we want to go through the image 0 all the way up to the image 9, and range 10 helps us count up that way. So we'll say images equals basically just this thing right here that we just created, except for instead of Y train equals 0, we're going to do Y train equals val so that we can iterate through the different values here. So we're filtering our data down to just the images that equal 0, and then 1 and 2 and etc. So now what I want to do is I want to plot all 10 of these images in a row, kind of like on their own row. So you know what, let's just try some of this stuff out down here. So let's say that these are our images, and let me go ahead and call this little plotting thing here. So I think it might be creating our image plot. There we go. Okay. So it took it a little while because it's trying to plot all these grids and everything, and all of these little X tick labels and Y tick labels and all of that. So we have 10 images here, and we want to plot it in this first row. Well, if we look at AXS and we look at AXS.shape, this is a 10 by 10 NumPy array of axis objects. So we want to grab the first row here because this is 0 that we're plotting for. So AXS 0, and then we want to go through and plot each image here. So maybe what we would say is we'd say for image in images, for image in images, what we want to do is we want to plot that image in the 0th index, the 1, 2, 3, 4, 5, etc. So actually, we need to wrap this in enumerate. Let's wrap this in enumerate, and that just gives us access to a little counter index here, I. And if you haven't used this before, play around with it. See what it does. Pause the video here for a minute and just tinker around with this. So we can say axis 0, I dot imShow, and now we have access to our image here, our image, which is a NumPy array. So we're going to call dot reshape 28, 28, and we'll call CMap equals gray again, and let's go ahead and turn off the grid once again. And let's set the x ticks to nothing. And let's set the y ticks to nothing. And you'll notice that the syntax can be a little different when you're using the axis object to plot rather than using PLT. So that can be a little confusing. So this is going to take another minute to plot. But whenever it does come up, you should see that now on the 0th row, on the first row, we've plotted all 10 of these 0 images. Look at that. That is perfect. That's beautiful. That's exactly what we want. So now what we're going to do is basically just copy this whole logic up here into this function. So now, rather than just doing this for 0, we're going to do it for all the values 0 through 9. So this val here is going to replace this 0 because now we want our row to be the same as the number that it's plotting. So 0 on the 0th row, 1 on the first row, 2 on the second row, like that. So let's give this a whirl. Let's try that out. Oh, and it looks like I did not call plt.show. So right here at the very end, after we've done all of that stuff, let's call plt.show. Oh, okay. Oh, we are just defining the function here. So that's why it's not plotting anything yet. It's because we haven't actually called the function. So let's do plot 10 images for each class. Let's pass in our x train and our y train data. And let's see what happens. Look at that. This is beautiful. This does not look like a 9. That looks very ugly, but that's okay. And this too, look at that. That's kind of scary. This is what our model has to learn. Our model has to learn to classify this as a 2, and this is a 9, and this is an 8, and all this kind of stuff. So this is definitely a hard problem here, but this is cool. We just created a helper function to show us some of the data. So this is looking pretty good. So because our data is cleaned, because it's already in a data frame and already good to go, we are actually ready to jump into some simple modeling here. And the first thing we're going to start with is a logistic regression. Now, I'm going to create a note here. This is very similar to what we did in the classic iris dataset course. And if you haven't taken that one and you think that it would be valuable for you, I would highly recommend it because we spend a little bit more time on logistic regression. But essentially what logistic regression is doing, is it's taking inputs and it's mapping it to an output classification. So in this case, our input is a row of pixels like this, and our output is a class label like this. We want to predict, hey, this is a 1. And this is exactly what logistic regression can help us do. So before even getting into neural networks, we can use a basic classification algorithm, a basic, kind of machine learning, non-neural network classification algorithm to try to approach this data set, because this is, after all, just classification with numbers. So let's go ahead and try that out. So I'll delete this cell. So I'll say from sklearn.linear model, so from scikit-learn, which is where a lot of our machine learning and statistics and modeling stuff comes from, we'll import logistic regression. And then from sklearn.model selection, we're going to import train test split because we need to create a training and a validation set here. So let's go ahead and run this. And like I said a little bit ago, you know, one of the foundations of machine learning and data science is that you never want to evaluate your model on the same data that you use to train your model. So we currently have our X train and our Y train, and we want to split this out into a group of data that we train on and a group of data that we evaluate on. So we use the train test split to do that. And I'll pass in test size equals 0.25 here. And if I just run this, function, what does it give us? Well, it kind of spits out, what are these? I think they're a few different data frames here. And specifically what it's giving us is it's splitting up our X train into an X train dataset and an X validation dataset. And it's splitting up our Y train into a Y train dataset and a Y validation dataset. So we just ran that, and if we look at, okay, well, first of all, what type of data did we get back? This is a data frame. Is our validation? Yep, that's also a data frame. Our YT, well, this is going to be a series because, let's see, let's look at our Y train here. Our Y train is just a series. This is not a data frame. That's just kind of a single dimensional pandas series there. So our X data, these are data frames. Our Y train and Y validation, those are pandas series. Let's look at the shapes of these to make sure that it split things out correctly. So this validation data set should be 25% of the total, and this should be 75%, and it looks like it is. Same thing with the Y train and the Y validation. All right, so now we have a way to evaluate our model on different data than we use to train our model. And this is exactly what we need. So I will go ahead and delete these cells using the X keyboard shortcut, as I like to do. So I'll go ahead and create a logistic regression model. So all we have to do to create a logistic regression model is just call, we instantiate the object like that. Easy enough. We've got a lot of, by the way, we have a lot of model parameters here that we could be playing with, but scikit-learn gives us a default value for all of these parameters. So just to get started, you don't need to know what any of these do. Now, if you really want to develop expertise in data science and in machine learning, then it helps to dive into each one of these and to get a deeper understanding of what's going on here. But to just get started, to go through a short course like we're doing here with the MNIST data, we don't need to dive in too deeply right from the beginning. It's better to kind of get your feet wet, and see what you can do. So now we call model.fit on our training data. So we pass in our X train, we pass in our Y train, and our logistic regression model is going to try to find how to map pixels to numbers. And you'll see here that we get a convergence warning. That's totally fine. We can try to deal with that in just a second. But our model is now trained. Our model has now figured out a way that it thinks maps pixels to numbers like this. So that is pretty interesting. Now, before we see how well our model actually is doing, maybe I'll put a little note here. Before we see how well our model is actually doing, what kind of accuracy would we get if we just randomly guessed? Or if we always guessed one number like 0. So, you can think about it for just a second. If we're just randomly guessing, And if we have equal numbers of images for each one of these, and this is actually something, let's take a look at this really quick. Do we have equal numbers? Let's look at ytrain value counts. It looks like our numbers are actually slightly off. So we do not have equal numbers of rows of data for each one of these. We have slightly more ones and slightly fewer fives. So this is slightly imbalanced here. It's not terribly imbalanced, but it is slightly imbalanced. So let's say that we guessed 1. We guessed 1 for everything. What would our accuracy for this guessing 1 model be? So what would our accuracy for the always guess 1 model be? And our accuracy would be, it would be 4,684 divided by, however many data points we have. So the length of ytrain. So our accuracy would be 11%. So this is something that's always good to do before you start evaluating machine learning models and statistical models. You need to start with some kind of baseline that says, before we start doing this in any kind of quote unquote smarter way, what's the dumb way? What is the silly way? What's the simple way that we could try this? And what kind of results do we get then? Because then we know if our model is doing less than 11% accurate, well, then we might as well just guess 1 all the time. We would have a better model if we just guessed 1 all the time. So this is very important. So I'm actually gonna give this a section header here, and we'll say, what is our baseline model accuracy to beat? All right, there we go. So now that we have done that, now let's look at our logistic regression model accuracy. And to do this, we can use the very handy model.score method. So model.score returns the mean accuracy on the given test data and labels. So in this case, test data, this is the data that we did not give to the model. This is our validation data. So XV and YT. So as soon as we run this, we are going to get the accuracy of our model on our validation data. So let's see how well our logistic regression model does at predicting the number based on the pixels. Let's see how well it does. Oh, found input variables with inconsistent numbers of samples. Oh, you know what? I put YT in here instead of YV. That was a big buildup for nothing there. All right, model.score. This is doing a lot better than 11%. This is actually doing 91.5 or about 92% accuracy. Now, that is pretty amazing given that we're just feeding in the raw pixels in a row here. So our algorithm is not getting the spatial representation of what this image actually looks like. The spatial distances are not being maintained. It's just getting a row of pixels like this, just a single row of numbers and predicting what the image is going to be. So this is actually pretty interesting, pretty incredible. But I think that we can do better with a neural network. And neural networks, indeed, specifically convolutional neural networks in recent years here have definitely become the norm for doing machine learning on image data. But I think we can do better with neural networks. So that is where we are going to head next. So I'll go ahead and add a little note here, by the way, which just says it looks like our logistic regression model trained on just the rows of pixels themselves gets around a 91 to 92% accuracy on unseen data. That's pretty impressive, actually. So before getting into neural networks in the code, I think it can be really, really helpful to get some intuition. So getting some intuition around neural networks. And the big site I'm going to point you here to, and this will definitely be in the course resources, is playground.tensorflow.org. So I'll go ahead and copy this into our notebook here. Save that, and let's take a look at this together. So this website is hugely helpful for helping you get an intuition around what neural networks are doing. So as soon as you load the page here, you'll see, it's got some of these little helper messages here. So this is the output from one neuron. Hover to see it larger. The outputs are mixed with varying weights, and if you hover over these lines here, that tells you the weight that things are getting multiplied by. And then here on this output square, so what we're trying to do here is given some input features, which in this case are just the x and the y axis, or here they call it x1 and x2. So just given the x and the y axis as our input data, as our features, we're trying to predict, or we're trying to learn a model that predicts if the dot is orange or if the dot is blue. And we have a few different data sets over here that we can play with. And all you do is you can tweak the number of neurons, the number of layers of neurons, and then you click play, and it trains the neural network. And you see this here, this epic, this is it training. And this data set pretty quickly, it solves it. Here's your test loss. So this is how bad is our network doing, and our network is not doing bad at all. As a matter of fact, it's classifying everything perfectly. So let's look at something harder. Let's take the spiral data set, for example. And if we click play, you'll see, okay, we're having a harder time here. Our neural network is having a hard time figuring out how to classify this spiral of data points based on just the x axis value here and the y axis value. So anyways, all of this is to say this website is hugely beneficial for helping you get a little bit more intuition around what exactly a neural network is. And as one starting place that I might suggest, start with 0 hidden layers. So you've got your 2 input features. These get multiplied by some sort of weight. And then you've got your prediction that you're trying to make. And start with this simple data set. And it's pretty interesting, actually. This is basically logistic regression. Actually, if you Google, neural network with 1-layer logistic regression here, let's take a look at this blog. You can actually show, that a neural network with certain parameters just is the same as logistic regression. So yeah, logistic regression classifier. So this website can help you get a sense, get an intuitive sense for what's going on when we train neural networks. And at the end of the day, it's just mapping inputs to some kind of output and figuring out how to do that. And all of these, the layers and the neurons, these are just little additional functions that help us do that. So I would highly recommend this website to you to play around with to get some more neural network intuition. So we are going to start getting into neural networks by just playing around with them here. So let's see, if we Google TensorFlow, Keras, MNIST, let's see here. So this Keras example, I think, is going to give us some good starter code to play with. So you can scroll down past a lot of the beginning stuff here. This is kind of some pre-processing, which we are not going to do for the time being. And right here, so create and train the model. So let's just copy this over into our notebook. So let's take a minute and just look through what this is. And we're really going to learn by experimentation here. If you're interested in the underlying theory behind neural networks and like building these things from the ground up, there are a lot of great resources online for that. We're not going to take that approach for right now because this is kind of a shorter course that's just intended to get you into it faster. And so we could spend the next 10 hours or the next 5 years on neural network theory here. But I want to get you playing with them and experimenting with them as quickly as possible. So to do that, we're going to start with this starter code from Keras. So first things first, have we imported TensorFlow? I don't know if we have. So TF here is TensorFlow. Let's go back up to the top and just double check. Okay, I don't think we have here. So what we can do is let's do import TensorFlow as TF. We run this, and it looks like it ran just fine. All right, so I'm going to create a little comment here for these 3 different pieces. So what is this? Okay, so step 1 looks like we are creating the model. Model equals something, right? And this something is actually where we specify the model architecture. So if you Google, neural network, let's just Google neural network. Let's look at some images. All right. So we have our input. This is the data that we're feeding in. And then we can specify any number of these layers in the middle, and those can have, really any number of neurons here, and they can be tied together in any kind of way we want. And then we have an output, and our output does need to be purposefully constructed according to what we're trying to solve. So in this case, we're trying to predict 1 out of 10 images, right? So we've got 10 different outputs that we need to account for. So what we need to do is we need to make sure that our input is good. We can specify however many hidden layers we want, and then we need to make sure that our output is good for what we're trying to predict. But otherwise, you see that, each layer here, this is kind of this vertical section of neurons, is composed of some number of neurons. So like this is hidden layer 1, and maybe this has 100 neurons in it, and this is hidden layer 2, and maybe this has 50 neurons in it, and stuff like that. You can see that maybe a little bit clearer here where, your input layer has a different number of neurons than your hidden layers here. Or here, your 2 hidden layers have different numbers of neurons. And we can specify that kind of however we want. So Keras, which is this, I'm not actually sure. It might be like a submodule within TensorFlow now. It's officially part of TensorFlow. Keras makes it very easy to specify those different layers. So that's what we're doing here, is we're specifying, this looks like an input. So this is kind of specifying the input layer. this looks like a hidden layer here. And then this looks like our output. So this first chunk here is where we are going to specify the neural network model architecture. And I might say, you know, taking care to ensure that our input and output layers match our data. All right, so we are going to need to make an adjustment to this here in just a second, but for right now, let's move on to this next block and just take a look at what this is. So we're kind of reverse engineering some example code from Keras here. And this is, honestly, this is a pretty good way to get started with a lot of these kinds of things that you might just be dipping your toes in. Is, you know, go out there, see if some code exists, play with it a little bit, and then you can work on diving into what's going on underneath the hood and really understanding this thing from the ground up, if that's what you want to do. But, you know, with a lot of these things, there is a lot to understand from the ground up. And if you really, really go deep, I mean, you know, you go all the way down to the hardware, and it's like, what does a GPU look like, and what kind of operations does it work with, and stuff like that. So you can really go as deep as you want here, or as shallow as you want. And I think somewhere in the middle is probably the best. But all right, model.compile. Now this step might not necessarily make as much sense as, you know, constructing the architecture of your model. That kind of makes sense. It's like, okay, well, we need to specify the number of layers and the number of neurons. This compile step here, well, this is where we're telling it, okay, how are we going to train this model? So whenever we train any kind of model, we want the model to predict the output correctly, right? But what does it know? Like, how does it know what's good and what's not good? And this is where we kind of specify that. So we specify that we're looking at accuracy. That's our main evaluation metric. And then our loss function, you know, essentially like how badly is our model doing? You know, we want some kind of function for, are we getting closer or further away from a good model? That's what this is saying. So our loss is this thing called sparse categorical cross entropy, which is good for, it's good for whenever you are doing multi-class classification like we are doing right now. And then optimizer, there are a bunch of different optimizers. We can just leave this with their recommendation right now using the atom optimizer. There's a whole field of optimization as it relates to neural networks and to other machine learning algorithms. So this is basically us telling our model how we want it to train. You know, how should it update all of the weights in our model? So let's think about how we want to put that here. So we might say, now we specify how we want TensorFlow to train our model. Specifically, what are our loss, optimizer, and evaluation metrics? All right. And then this one here, model.fit. So this is where we actually pass in the data. We tell it how many epochs we want to train for. So this is kind of how long we want it to train for. It's like how many times through our data we want to train. And then we give it some validation data. And remember, this is based on that kind of golden rule of data science that, you know, you don't want to evaluate your algorithm, your model, on the same data that you used to train it with. And we're going to need to make some adjustments to this as well, because our training data and our validation data look a little different. But for right now, we can say this is where we actually fit the model and figure out what the best model weights are to give us accurate predictions. Okay, so I'm going to go ahead and split these three things out into their own cells so that we can play with them individually. So, by the way, I like the keyboard shortcut A to insert a cell above, B to insert a cell below. You can use X to delete a cell. These are things that make working in Jupyter Notebooks much speedier, which is nice. So, all right, so we have these things in their own cells now, and let's tackle them one by one. So if you notice here, let's go into this example where we're pulling this code from. So so this data here, the reason why they have this tf.keras.layers.flatten, and you see this input shape 28 by 28 by 1, is because they have their data structured in this square image format here. So this first layer is actually just taking their data, which is in this two-dimensional format, and flattening it. That's what the layers.flatten does here. So I believe we can just delete this for now because our data, it starts out flat, right? Like we have to structure it into a square in order to plot it like this. So we don't need the flatten layer. And then this last layer, this is what I was talking about whenever I said we need to make sure that our output is the correct size. And that's this dense 10 activation softmax. So this basically means at the very end, we want to output a probability distribution of what we think the answer is to what digit it is. So if we just Google softmax, let's look at softmax neural network. Let's try this. Here we go. So this is a really good image representation of that softmax. So we have our image, and this actually looks like it matches up pretty closely with what the Keras code is doing. So we have an image, we flatten it into this flat layer of neurons here. We send these numbers through this network, and all these lines here are different weights that you're multiplying everything by, and you're just doing a bunch of calculations here in the middle. And then at the very end, in this problem, it looks like we want to classify, is this a dog or is this a cat? And the softmax, what that does is it outputs a series of numbers that add up to 1 that give you the probability of the output being one class versus another class. So in this case, there's a 95% probability, 0.95 probability that this is a dog, 0.05 that this is a cat. You notice that these numbers sum to 1, which is what we want for a probability distribution. We want the answer to be one of these two. There aren't any other options here. It's just either a dog or a cat. As far as how we've specified the problem. So that's what the softmax is doing, is it takes up all these numbers, and no matter what values we end up with here at the very end, it transforms them into numbers that add up to 1. So in our case, rather than having 2 numbers that add up to 1, we're going to have 10 numbers that add up to 1 because we have 10 different digits that we could be outputting here. So let's go ahead and run this cell. And one quick note, you'll notice that we also have 128 neurons here in this middle layer. So that's what that means. And Keras, thankfully, is smart enough to connect up all of the inputs and the outputs together. As a matter of fact, we don't even need to specify the input size because it takes care of that automatically for us. And it connects these 128 neurons to these 10 neurons and does all of that complicated math and coding behind the scenes. All right. Now, this cell is looking good. Our sparse categorical cross entropy, we're pulling this code directly from something that was used to fit a model to MNIST. So I think these are going to be good settings to go with. Let's go ahead and run this. So we compiled our model. We told it how we want to optimize it. All right, and then the last thing is to edit this cell down here. So let's look at model.fit. Let's look at the documentation here. So model.fit. So we want to pass in an X. We want to pass in a Y. So let's go ahead and start constructing this because we are going to need to make a couple changes here. So our X train data, let's go up here, take a look at. So we've got this XT and XV and YT, YV. We could use these. We could also use X train and Y train. Okay, so we have a couple options here. So let's look at the documentation again. So X equals something, Y equals something. We've got a batch size. We have epochs, which is how many times the neural network is going to process our data, trying to find the right model. So this is essentially how long we're going to run it for. And then you see down here, so here they use validation data. We could also use validation split. So there are a couple different ways that we could do this here. So I think to start with, why don't we pass in our full X training data? Why don't we pass in our full Y training data? And I think that these might still be, yeah, so this is going to be a pandas data frame. Typically things want NumPy arrays, so let's pass in dot values to pass in those NumPy arrays there. Let's pass in epochs, and we'll just leave that as 6 for right now because that's what the example started with, so that's a totally fine default. And now let's pass in validation split. So rather than passing in the validation data, we're just going to pass in the validation split, and it's going to take care of doing that for us. So let's say maybe like a quarter of our data will be used for validation. All right, and let's go ahead and exit out of this. And I'll go ahead and copy this comment down here. We can delete this cell. And I think we might be ready to fit our model. So let's go ahead and run this cell. And if we've done things correctly, we should see this start to happen. So our neural network is now training. So you'll see epoch 1 out of 6, epoch 2 out of 6, 3 out of 6. So each time this runs through an epoch, our neural network is going through our data. It's basically calculating our loss. So it's calculating how good or bad our model is. And then it's going to go back through and update all of the weights inside of our model to try to get a better model. And it's going to give you an output of how well it's doing throughout this whole process. So let's take a look here. Let's analyze this output. So first of all, it gives us our loss. So this is that measure that we defined up here. This is essentially how bad our model is, where a bigger number indicates that we are further away from a good model. So a lower number indicates a better model here. So you'll see that this loss decreases as we train. And by the way, this is our training loss. So this is the loss based on our training data. And over here, you'll see val loss. So that's our validation loss, which is the loss based on our validation data. And we're going to use both of these in conjunction to determine if our model is overfitting, if it's underfitting, how we need to tweak things here to get better model results. So first of all, you'll notice that the training loss decreases with each epoch. That's what we would expect. The accuracy increases with each epoch. So you'll see we start here, our very first epoch, with an accuracy of about 85%. So if we scroll back up to our logistic regression, we were getting 91, 92% accuracy with our logistic regression model. So that was kind of our initial simple model baseline. Now, our accuracy goes up to, down here with the neural network, epoch 2, to 90%, to 92, 92.7, 93%, and we end up right around 94%. So even with this basic model here, this is one hidden layer, so a little bit more complex than our original logistic regression, we're ending up with a few percentage points higher accuracy. And remember, this is our training data. So let's look at our validation data, our validation loss. So you'll notice here that the validation loss does decrease, but it hits this 0.42 and then bounces back up and then back down. This might be an indication that our model right around here has learned kind of all that it's going to learn. And actually, let's take a look at our validation accuracy. So you notice that our validation accuracy, unfortunately, it kind of prints around the edge here, so it's a little bit harder to read. But validation accuracy starts at 86%, 90, 92, 91.7, 91.6, 91.7. So it does look like our training accuracy, even though that keeps going up, our accuracy on unseen data here stabilizes right around 92%, which actually is kind of in the ballpark of what our logistic regression was getting. And this might be a sign that after epoch 3 or 4 here, our model is actually just starting to overfit. Our training accuracy keeps going higher, but our model doesn't do any better on unseen data. And remember that the evaluation on unseen data is really the most important thing that matters here. So we have some good knowledge just from looking at these numbers, but is there a way that we can capture this data and plot it, for example? Well, if you notice that TensorFlow output at the bottom here, this callback.history, this indicates that it returned something that we didn't capture in a variable. And I know from working with this before that if we write history equals here, let's assign this to a variable. Let's rerun this again. Now we're going to capture that training history, and then we'll be able to use that to plot our training accuracy and our validation accuracy. So there we go. Our model finished training again. Let's take a look at this history variable. Let's see what we just captured here. Oh, well, this is exactly the same thing that it returned previously. So if we look at the type, this should say, callbacks.history. If we do history dot and then hit tab, let's see what we have access to here. So we've got epoch, 0, 1, 2, 3, 4, 5. We have history. There we go. And this is what we're going to want. So history.history gives us access to a dictionary that has our training loss, training accuracy, validation loss, and validation accuracy for our different epochs. So let's go ahead and plot that. So I'm going to, let's create a new section header here, and I'll just say plotting learning curves, which is what these are called, for our neural network. All right. So let's take a look at our training accuracy here. So history.history, and then we'll access the accuracy key. And let's see here. Now, what if we want to do plt.plot? So let's plot this. But now we can't. Oh, well, yeah, we can just plot this. Looks like it just plots that with an x-axis of just kind of the epoch here. They're just the numbers, which is what we want. So that looks good. So this is our training accuracy, I believe. Let's give it a label. Training accuracy. Now let's plot our validation accuracy. We'll do validation accuracy. Now if we run these, we'll see that it's plotting these two in the same graph, but we want a label to show up. We want a legend here to tell us which one is which. And maybe we also, let's go ahead and give it a title. So we'll just say training versus validation accuracy. And I'll put plt.show down here. And you'll notice that our y-axis is very zoomed in here. So there's a question of, do we want that? Let's try it with a y limit from 0 to 1. Well, this is pretty interesting. You actually see that with a y limit of 0 to 1, it's extremely difficult to tell any difference between these two lines. So maybe we want to zoom in a bit. Let's try, we could either try the default that it gives us, or maybe we zoom in to 0.8 to give us a little bit of perspective here. All right, so now we're looking at our training versus our validation accuracy. And you will notice that our training accuracy does keep going up ever so slightly. And it's not very drastic. We start out pretty close to where we end up, honestly. But it does keep going up slightly. And our validation accuracy kind of bounces around, but then maybe even decreases a little bit towards the end. And although the effects here aren't very big, this is a classic sign of overfitting. So overfitting is where, you know, you keep training, and you're learning your training data better. But what you're really doing is you're really fitting to the noise at this point. You're not generalizing any better to new data. As a matter of fact, as you go on, you're going to get slightly worse on new data because you're fitting to the noise. So just for people who might not be as familiar with overfitting and underfitting, there's a great image that I think captures this. Here's a great one. So you have, let's say that you have this data set here, and you're trying to learn a model that characterizes this data pretty well. Well, you and I can look at this and kind of draw a line through the data points that we think looks good, right? You know, it's this line right here. It's kind of this parabola. So an underfit model is one that's too simple. In this case, a linear equation, you know, y equals mx plus b, is not going to capture the pattern that we need to match here, because our data isn't linear. You know, it's nonlinear here. It's got this curve in the middle. So this is underfit, when our model is too simple. It's not capturing the information in the data. Versus overfit, this is going the other way, where it's capturing too much of the information in the data itself. It's capturing too much of the noise. So you and I can see that, you know, if we draw little lines between every single one of these points here, well, now we're not really fitting the overall shape of the graph. We're starting to fit some of that deviation here. And that's being too flexible. So what we want our model to look like is right here in the middle, where we capture that underlying signal, that underlying pattern, but we're not capturing that random noise around either side of our pattern there. So this is underfit, too simple, not capturing the signal. This is overfit. It's too complicated. We're capturing both the signal and the noise. And what we want is this good, robust model right in the middle, where we're capturing just the signal and we're not fitting our model to the noise. So, and that's why, if you notice, actually, let's go back to this really quickly. If you notice that if you have a loss function for this graph on the far right here, this graph, this model will actually appear to show a lower overall model error. And why is that? Well, it's because it's getting closer to every single data point. I mean, this model is doing a better job of predicting the training data. The problem is this model will not do as good of a job of predicting new data. And so that's why it's so crucial that we don't just look at the training error, because this training error, you know, we can get that down to 0. We just draw a line through every single point, and then our training error is 0. You know, it's like we've perfectly fit our data. But as soon as you start giving us new data points, that's where we're gonna be in trouble. And so this model here will do not quite as well on the training error, but it will do better on the validation. And what we want to do is we want to find that good middle ground where our training error or our training accuracy and our validation accuracy end up at right about the same place, where our model is nice and robust, not overfit and not underfit, but perfectly in the middle. Now, we might also want to look at our training and validation loss. So this is just kind of another way of looking at, approximately the same information. It's another way that we can help assess our over and underfitting. And we might want to create a function to plot these together so that as we're training additional models and seeing how they do, we have a quick way to plot our results. So let's go ahead and make that happen. So the first thing I'm going to do is I'm going to start out as we did before using plt.subplots, and I want one row of images and I want two images in that row. And now for fig size, maybe I'll specify maybe like a 10 by 5 image grid or something like that. And if we go ahead and run that, we can see what this will look like here. So that's looking pretty good to me. And let's look at our AXS, our axes, and we see that we have a NumPy array, which is just one-dimensional. It's just got two axes in there. So we know AXS0.plot is going to be one of them, and then AXS1.plot is going to be the other. So maybe let's make this first one our training and validation accuracy, and we'll make the second one training and validation loss. So let's go ahead and plot. Here we go. I'm just going to copy down this whole block, and we'll make adjustments as needed. So AXS 0. So let's do this. plt.soupTitle. This is something that needs to happen at the level of the full graph. So I'll put this down here at the bottom. I'll go ahead and throw plt.show down here as well. And then we can set the ylim if we want. All right. Let's just go ahead and run this and see what happens. Oh, okay, so we see axes subplot has no attribute ylim. This is what I was saying before, where the way that you call these things can be a little different from PLT to the axis. So let's try that. And there we go. This is looking good. We have our legend here with our training accuracy, our validation accuracy. We're going from 0.8 to 1. And we have a title over our full graph, although this is now training versus validation accuracy and loss. So there we go. And now we can just copy this whole block here, change all these axis references to the first index. We don't need the ylim currently because we haven't looked at our loss yet. So let's do loss and val loss. So this is going to be training loss, validation loss. Let's check this out. There we go. Look at that. So it looks like our training and validation loss here. So what is this? Validation loss, training loss. So our training loss is lower. That's what we would expect. Because once again, we usually expect our training accuracy to be higher and our training loss to be lower. But if that happens too much, then we know that we're overfitting, which it looks like, we might be slightly here. Maybe we want to set this ylim to 0. So let's see if we can do that. AXS1.set ylim. Let's set that to 0. So that minimum is now 0. So this is looking pretty good. So now, rather than just doing this once, let's wrap this up into a function. So we'll say def plot, we'll say training and validation curves. Training and validation curves, yeah. We'll just go with that for now. And maybe we'll just pass in this history object. Pass in this history object. And let's just start with that. That looks good to me. So now we have a generic function that we can call later. And let's go ahead and call this plot training and validation curves. We'll pass in history, run this. This is looking good. So now if we train a new model and we get out that history object again, then we can just pass that into this function and get our nice training and validation accuracy and loss curves. All right, now comes the fun part where we get to just experiment with different neural network architectures here and see how they do. So I am going to, let's create a new cell here just so we can kind of copy paste some stuff up here. So, all right. And since we're just experimenting now, I'm going to remove these comments. All right, so in this one cell, now I'm going to copy paste this down below. And let's create a new markdown cell, and I'll say, maybe we'll say experimentation with different architectures. All right, so we'll create a new model each time. We'll compile it each time, and each time we'll fit the model. We'll get a different history, and then we can plot it out here at the end. So let's go ahead and just drop our plotting function right in there and see what happens. So let's bump up the number of epochs. I'll bump it up to 10 for right now, just so we get a little bit more training time here. And what happens if, for example, let's take this neural network architecture here. Let's just add another layer, just another dense layer of 128 neurons. So we're going to make our architecture a little bit deeper now. So now we've got 2 hidden layers. Each one of them has 128 neurons. They're connected to each other. They both have the rectified linear unit activation, which you can definitely learn more about this if you want to know kind of what's going on there, but this is getting into more of the underlying theory of neural networks. And you know what? Let's just go ahead and run this and see what happens. So one thing that you might notice, and I don't think we're really noticing it yet, but as you make your architecture bigger and more complex, this training time here might take a little bit longer. So I'm running this on a CPU currently, I believe, because I'm on a MacBook, and I don't think TensorFlow integrates with the GPU nicely on my hardware. So if you have a GPU, this could potentially run a lot faster. But just something to be aware of, that as you make this more complex, it might take a little bit more time. It will take a little bit more time. So, okay, so we just added another layer to our network. And this means that our network is going to be able to capture more complicated relationships in the data. So let's see what happened. So our loss decreasing down here, our accuracy, you notice our training accuracy going all the way up to 97%. And let's take a look at our validation accuracy. Well, this is actually going up to 95, almost 95.5%. So this is a significant improvement over what did we have previously? Validation accuracy of like 93%. So, and this one's like 94. So that is definitely an improvement. And if you notice here, both our training accuracy and our validation accuracy are getting better over time. And they don't actually look like they're too far apart from each other. They're a little far apart there at the end, but it doesn't look like they're diverging too much. So let's take this. Let's actually just try running this model for more epochs and see what happens. So let's try, I'm going to try 30 epochs here. I'm going to run this. It's going to take a few minutes, so we'll come back whenever that's done. Okay, so that just took a couple minutes there. You'll see if we expand out this whole training section that we've got 30 epochs, and it's giving us the data for all of this. But let's just take a look at this final graph here. I'm going to go ahead and actually kind of collapse this cell. And so now you'll notice that we're starting to see some of the more telltale signs of overfitting here a little bit. So what's happening is that you notice this training accuracy keeps getting better and better and better over time. Not by much, but it does keep getting a little bit better. And the training loss keeps going down to 0. But at some point, the validation accuracy is starting to level off, and it's bouncing around a little bit. It's not meaningfully getting better over time. And you can definitely see that here too with our validation loss, where you see it kind of levels out and doesn't seem to be making any noticeable improvements, even though the training loss keeps going down. So this is really that classic look of overfitting here. On the left side, this would be what underfitting looks like, where it's like both of the losses are high, the accuracy is low. If you let it keep training, it does keep getting better. So the best model is going to be found somewhere here in the middle, and you'll often hear people talk about kind of like the elbow method. So what is the elbow method? Well, if you imagine an elbow and you imagine the crease right in the elbow, that's, that might be where you want to look for a good model here. And you definitely want to pick one. You want to pick a model before the validation loss starts coming back up, because that means you're doing worse on unseen data. So this is pretty interesting. And by the way, whenever I say pick a model, we'll go over what that means in just a second, because the model that we're left with here at the very end is the model after all of this training. So the model that we have right now is an overfit model, and we would not, it's not that bad, but we probably would not want to use this as our final model. We would want to go back to whatever the model had been at one of these previous stages. And there are a couple techniques we'll talk about for doing that in just a minute. But for now, let's do more experimentation. So I want to add another layer here. Let's just add another. Let's add another 128 neuron layer here. So we're just going to make this thing even deeper. And by the way, notice that we aren't using any kind of special neural networks like convolutional neural networks right now. We're not actually going to touch on those in this course, just because this is kind of an introduction to neural networks. We're doing this all in a single Jupyter notebook. We want to get through it pretty quickly. So we're not going to be using anything special like convolutional neural networks. But doing other vision stuff, we would definitely want to experiment with that as well. But for now, let's just make this deeper and see what happens. So I'm going to go ahead and run this again. We'll let it run here, give it a couple minutes. It will plot the results, and we'll come back in just a sec. All right, so that just finished training. So let's take a look at our results here. So by the way, what was the peak validation accuracy that we achieved here in this prior run? So it's going to look right around, 90, maybe 96%. If we see here, we see, okay, 96.5. I'm not seeing anything here really above 96.5% validation accuracy. So let's see how our new one did. So we go down here, validation accuracy starts around 90. It's coming up to like 95, 94, 95. We get to 96. So this is epoch 15. We're at like 96.5. 96.5, 96. So it looks like, oh, and then actually if we let it keep going a little bit, 96.3, 96.7, And then we do jump up above 97. You know, this could just be kind of a random variation here as we're going through this. So we might not be able to consistently get 97% accuracy. But we are getting consistent like 96.5, 96.7% accuracy. And we did go above 97% accuracy there with our validation accuracy. You notice here that by the end, we are overfitting again. So our training accuracy is up right around 99%. And that would just, you know, keep getting better the longer we let it train. But our peak validation accuracy here is achieved somewhere right around maybe epochs. I mean, really, we hit 96.5 for the first time at epoch 16, but we might do a little bit better by letting it train longer. It's kind of hard to tell here. We might want to go earlier, stop it earlier. So this actually does lead to the next topic, which is how do we access those models that do better? Because right now, you know, after 30 epochs, we do have an overfit model. We really just want to train it for, you know, somewhere in between like 15 to 20 to 25 epochs here until we get that nice model that's in the middle where we're not overfit. So there are a couple different approaches to doing this. The one that we're going to touch on really briefly here is called early stopping, and it's just exactly what it sounds like. You stop training your model early, so you don't let it run the full number of epochs that you've specified. You give it a criteria to say, okay, I want you to stop whenever my validation accuracy stops going up. But now, since our accuracy is kind of bumpy, we might not want it to stop immediately whenever the validation accuracy stops going up. We might want it to wait a little bit just to see, okay, was this just a bump? Are we still on average increasing our accuracy? And there are ways to do that. So this can be achieved with something called a TensorFlow Keras callback. And so if we do TensorFlow.keras.callbacks and then hit tab here, you'll see early stopping is one of these. And so let's look at the documentation for early stopping. So we add something for early stopping to monitor. So in this case, we would probably want to do the validation loss, just like it's specified. And then it's got some other parameters here. So one that we might look at is patience, or the min delta here. But let's take a look at patience really quickly. So patience, this is the number of epochs with no improvement after which training will be stopped. So if our patience is 0, which is the default, then as soon as the model stops improving based on our validation loss, then the training will be stopped. But maybe what we want to do is we want to give it like a patience of 1 or a patience of 2 or something like that, so that if there's a little bit of fluctuation, we don't stop it too early. So what we do here is we create this. You know, I'll just go ahead and pass in monitor val loss, even though that is the default, just to be explicit about it right now. And maybe let's say patience equals, we'll set patience equal to 1 or something like that. And we'll set this equal to early stopping here. And now what we do is let's copy this model down here. All we do is add ES, and I'll say early stopping. We add this to a parameter in our model.fit. Our model.fit method here called callbacks. Callbacks, I believe is what that's called. Callbacks equals, and then we pass it a list of these callbacks. And in this case, we just have one callback. That's early stopping. And now what will happen is our model will use this callback to monitor the validation loss. And after the validation loss stops improving, you know, with this patience of one epoch here, then it will stop training our model. And in this way, we can help to prevent overfitting. So let's go ahead and train this, and we'll see what epoch it stops at, and we'll also see what our training and our validation curves look like when it's done. All right, so we just finished training here. It actually stopped it after 10 epochs. So 10 epochs was, let's take a look at our validation accuracy here. So we went from 95.2 to, I'm just converting these to percentages in my head, kind of, by the way, but 0.952. So 0.952 to 0.9521. So we went down a little bit, went back up a little bit, 0.956, so we went up a little bit more, 0.9563, so it went down just a little bit. So it actually stopped it earlier than what we were talking about. We were saying, maybe somewhere in the 15 range, maybe somewhere in the 20 range, but it actually stopped it back here. And this is something that we might be okay with if we want to be on the safer side. We want to make sure that our model is not overfitting. And so we're going to cut out some of this variation, which may or may not be good for our model. And if we look at the accuracy that it achieved, so 95.6% accuracy might be a little bit lower than what we were getting previously, but we can also feel pretty confident that we're not overfitting too much, or that we're not really overfitting here. Our training accuracy is a little bit higher, so maybe we are still slightly overfitting a little bit, but definitely not as much as up here. So that's what early stopping does. And now our model, so this model right here that we have, model, this is going to be a pretty good fit model. So we're going to move on now to looking at what's called a confusion matrix. And basically, where is our model predicting things correctly? And where is it not predicting things correctly? I'll create a new section header here, and I'll call this model evaluation confusion matrix, etc. Okay. So what is a confusion matrix? Well, a confusion matrix, let's Google it really quick. Let's look at some images. So here, we see some nice examples of we're essentially creating this matrix of what did we predict? So we predicted a 0, and what was the actual? And we're counting up the number of predictions that fall into each one of these categories. So here's an example of something actually that's going to look very similar to what we're going to create. This might even be on the MNIST dataset. It's kind of hard to tell, but it does have 10 classes here. So for example, we want to predict a 0. Did we predict a 0? So predicted class, we predicted a 0. Was it a 0? There were 38 data points for which we predicted a 0, and it was a 0. And in this case, it looks like we got all those, this image got all of those perfectly correctly. So then let's take a look here. Maybe we predicted a 5. We predicted a 5, but the actual was a 6, and we had one data point that was true for. So this would be a misclassification. And if we start seeing some patterns in our misclassifications, then maybe we have an idea of where our model is not doing as well. And that might be a place where we want to get more data, or where we want to do some feature engineering or something like that. But we need to understand kind of where things are going wrong. So we have our model, and this is the model that we've picked based on its validation accuracy and validation loss. So we're going to do something here. The golden rule is don't evaluate your model on the same data that you used to train with. We might fudge that slightly here by predicting values for X train. And the only reason why we're going to do this is we want to look at where we're misclassifying things. So if we wanted to be, strictly accurate about this, then maybe we would do, an X train, X validation, Y train, Y validation split, and we would, do model.fit with early stopping, on our X train and Y train. And then we would do model.predict on our X validation data. So if we wanted to be kind of strictly accurate here, this is what we would do. But since we've already chosen a good model that we think is good based on the validation accuracy, and we just want to get a sense of where it's misclassifying things, I'm comfortable with making these predictions and checking out those misclassifications using our full training data set here. So I'll call this ypred, and we're just going to do model.predict. And let's take a look at ypred really quick. So what is this? So ypred is going to give us, let's take a look at the shape, and let's look at the shape of what we passed in. So this is where you can really see that softmax coming into play now. So we have 42,000 rows of data. We have 42,000 images that we're working with in our X train here. And our predictions, we get 42,000 predictions. So that's exactly what we would expect. But why do we have 10 different values here? So let's take a look at the first row of data. So you'll see a lot of scientific notation here, e to the negative whatever. So can we do a dot round? Let's round it to like 4 decimal places. So wow, even if we round it to 4 decimal places, can we round it to like 10? Nope. We can't round to, yeah, if we round to like even 20 decimal places. So this scientific notation is actually just kind of a way of masking. It's hiding what's really going on here, which is the fact that one of these values is basically a 1, and the others are basically all 0. So our model is very, very confident that this value here is this would be a 1, I believe. So ypred 0, it's predicting as a 1. And let's actually, let's just take a look really quick and see what the actual y value here is. And the actual y value is a 1. So in this case, we're predicting correctly, and our model is very, very confident. So, and if we sum this, then you'll see that it sums to 1, and this is what we were saying it should do, because the softmax function in our model here is outputting a probability distribution where everything sums to 1. And it's essentially the probability of this data point, the first data point, belonging to each different class here. So how can we get the prediction whenever we have 10 different numbers here? So we want to find the index where that maximum value is. So in this case, if we round this, we can see that this is the probability of it being a 0. This is the probability of it being a 1. We want to get this index here. So this is the first index, the 0th index, first index, second index, etc. So the way that we can do that is we can use the np.argmax method. And this returns that, hey, the maximum value in this NumPy array here is at the first index. And now let's try this for, data point 1, data point 2, data point 3. So by doing this argmax, we're going to get what that prediction is for each row of data. Now, if we call argmax on this whole thing, you notice that it still just returns a single value. But hey, we're passing in the full data set here. We're passing in all of our predictions. Why are you just giving us a single value? And that's because np.argmax can also take in this axis parameter here. So right now it's telling us where is the maximum value in our whole two-dimensional matrix here. So what we really want is we really want the maximum value for each row of data. And to get that, we pass in axis equals 1. And this essentially says, give me the index for the maximum value at every single row. And just to verify that, we can look at the shape, and we should have 42,000 predictions, which we do. 42,000 different argmaxes here. So in this case, we can set ypred classes equal to this argmax. And now ypred classes, let's look at those first 10 predictions. And let's look at the first 10 predictions for our actual values. And let's see, okay, check this out. We're predicting a 1, it is a 1. We're predicting a 0, it is a 0. We're predicting a 1, a 4, a 0, a 0. We actually get all of these first 10 ones correct. So how do we, how can we see where we are messing things up? And this is where the scikit-learn library can come in handy. So if we say from scikit-learn.metrics import, I'll hit tab here, and we have a whole bunch of different metrics that we can import, including confusion matrix. So let's go ahead and import that. Now, if we take a look at the documentation here, confusion matrix, question mark, shift enter to get this documentation. So confusion matrix, it says compute the confusion matrix to evaluate the accuracy of a classification. And that's exactly what we're doing here. So we need to pass in the yTrue. These are the true classes, the true digits that we're recognizing. We need to pass in the ypred, the predictions. And then we've got a couple other parameters here that we can pass in if we want. We don't need to pass in anything now. And then what does it return? Well, it returns a NumPy array, a multi-dimensional array of shape in classes by in classes. So a 10 by 10 in our case. All right, so let's go ahead and run this. And I'm going to call this conf_mat. So confusion matrix. We pass in our prediction. Let me make sure I'm getting the order right here. Getting the order right. Oh, we pass in the true, and then we pass in the prediction. Okay, so yTrue. So we'll pass in yTrain.values, and we'll pass in ypred classes. Now, if we take a look at our confusion matrix, we get this lovely thing here. So this is giving us a lot of information, but first we need to figure out what are our columns and what are our rows. So I'm going to Google scikit-learn confusion matrix. And this is a little, it can be a little tricky here. By definition, a confusion matrix C is such that Cij, so I is the row index, J is the column index, R by C, rows by columns, is equal to the number of observations that are known to be in group I. So our rows then are our actual values, and predicted to be in group J. So our columns, these are our predictions. So I'm going to put a little note here. Rows are the actual values. Columns are the predicted values. And the value in that cell is the number of predictions that meet or that have that characteristic. All right, there we go. So, but I want to go ahead and just turn this into a pandas data frame so that we can see that a little bit better. So the way that I'm going to do that, let's make this into a pandas data frame. So if I do pd.dataframe and just pass in conf_mat, Well, what does that do? That gets us a little bit closer. Doesn't quite get us what we want, though. In particular, we want the columns to be, showing us that we predicted this, and the rows to say this was the actual value. So the way that we can do that is we can pass in a list for an index and a list for the column names. And let me go ahead and just create this really quick. So column names equals, let's do a little f string here. We'll say predicted I for I in range 10. And just to show you kind of what this is doing, column names here. So there we go. You see predicted as a 0, predicted as a 1, etc. So we'll pass that in as our column names. And then our index, or maybe we'll call it our row names. So that's just going to be the same thing, except for we're going to say actual. So maybe we'll say predicted and actual here. And then for index, we'll pass in row names. And we'll set this equal to readable conf mat, so readable confusion matrix. And let's go ahead and delete this and this. And we'll run that. And now let's look at our readable confusion matrix. There we go. So now we can very quickly tell, okay, we predicted a 1, and when was it actually a 1? Okay, well, that's actually, most of the time. Maybe we want to get a sense really quickly, because we can look around here and say, okay, which of these did we have a hard time classifying? And it looks like we've got some big numbers here. We've got some big numbers here. So there were a lot of times that we predicted a 2 when the actual result was a 7 or an 8. There were a lot of times we predicted a 4 when the actual result was a 1, a 9, a 6. There were a lot of times we predicted 9s when the results were actually 3s and 8s. But you'll see that this diagonal here, this diagonal is showing us that for the most part, our predictions are spot on. We're getting the predictions correctly. All right, so now one more thing that I want to do here with this readable confusion matrix is, what if I want to tell at a glance, where we're misclassifying things? Well, there's this really nice Seaborn. So Seaborn is a data visualization library. It uses matplotlib, but it can do some fancy things pretty easily, and it creates some pretty beautiful looking graphs here. So there is a SNS or Seaborn heat map here that we can use, and if we just pass in our matrix here and run that, you see that this provides a pretty nice way of immediately highlighting where the big values are. So it creates the color here based on the value in our data frame, in our matrix here. Now, the only problem with doing a heat map currently is that these diagonal values are so big that we can't see anything else. We can't see what's going on here. So maybe we want to get rid of these diagonal values just to see where those misclassifications are happening. So one way that we could do that, let's say for I in range 10, maybe we want to do readable conf mat dot index location I comma I. We want to set that equal to 0. Let's take a look here. And I believe that worked. So really quickly, what we just did here was we looped through the numbers 0 through 9, and then we used the pandas. So iloc, this means index location or index locator. And this just basically means we want to identify a row and a column based on the numeric index. So we want to go to the 0th row, the 0th column, and we want to set that equal to 0. Then we want to go to, if I equals 1, we want to go to the first row and the first column, and we want to set that equal to 0. So that was just kind of a nice shortcut way of setting the diagonal equal to 0 here for our readable confusion matrix. And now, if we run this again, now you can see really where those hot spots are that we misclassify things. So we misclassify very often. We predict 4s and we actually get 9s. Here looks like our next big hotspot. We predict 6s and they were actually 5s. You can kind of see how that might happen. And we could look at some of these misclassifications if we wanted to, but this is giving us a sense of where are we misclassifying things. And this is helpful for going back and tweaking the model, doing some feature engineering, all of those kinds of things to figure out how to make a better model that gets a higher accuracy. Unfortunately, though, I believe that this is where we are going to stop for now. I want to keep this nice and short. There is so much more that we could do here, but that is always going to be true. You can really go as deeply into this as you want. There are so many different paths for exploration and for learning. So we are going to go ahead and stop here. So let's wrap up really quickly, and we could say final evaluation of our model. And this is where we actually have kind of like the little surprise that our test data set, do you remember our test data set here at the very beginning? So this df test had one fewer column. So let's look at that really quickly. df test.head. If you remember, our test data set did not have the label with it, and that's because this is coming from this digit recognizer competition on Kaggle. So Kaggle competitions, they will give you a test data set for you to create predictions based off of, and then upload them, and then they kind of provide like a leaderboard to say, okay, we're just going to show you your score. We're just going to show you your score on this data, and we're not going to show you what the actual answers are so that we can evaluate your model. And this is how competitions on Kaggle work. So we're not going to get a final evaluation score on our test data here because we don't have the true labels. But I would encourage you to make predictions here, create a submission, upload it to Kaggle, and see how you do. See how well your model here has done, and you can see if you can get a better model. See if you can improve your model accuracy. So, since we don't have the true labels for our test data set, our final model accuracy will go off of our validation accuracy from training our neural network. And this is fine, by the way. Since we're looking at a validation accuracy, this is the accuracy on unseen data. And so this is a totally fine way to evaluate your model. I would highly recommend that you, a data scientist watching this video right now, that you create predictions from the test dataset, upload those predictions to Kaggle, and see how well you do. Then maybe try iterating on your model and see if you can do better. All right, and with that, I hope that you have learned a ton. I hope that you have had a good time doing this course. And most importantly, I hope that you maybe have some ideas for what to learn going forward in the future. Um, like I said, there's so much here to learn. There's so much really exciting knowledge in the data science space. And this is you just kind of dipping your toes into neural networks, dipping your toes into image data science. And I hope that it sparks an interest for you to continue looking at other things and playing around with this stuff yourself and learning it yourself. And maybe taking a few more courses on project data science as well, so that I can help walk you through learning about other topics as well, and going deeper into some of this stuff. So with that, I want to say thank you so much for taking this course, and happy learning. All right. Thank you so much. See you later.